So, welcome everybody. It's my great pleasure to have here Richard Bamler giving a talk today, and he will talk on Ricci flows in higher dimensions. Please.
All right. Well, yeah, thank you for giving me the opportunity to speak here. Today's talk will be the first time I'll give this talk, and it's about new work, so I apologize if this talk is going to be a bit rough around the corners. Also, as I said, I don't plan on covering all the slides in this talk. I think there are going to be too many slides, so I'm okay cutting this talk short. And if you have any questions, please just either mute yourself or write in the chat. I hope I'll catch it. And I think it's better to address questions sooner. Also, I wanted to take the opportunity to make a small advertisement. So, as you know, we're still on lockdown here in Berkeley, and we will have the entire semester online. And I'll be teaching a class at Berkeley on Ricci flow this fall semester. And if you're interested in attending the class, just email me. I can provide you the Zoom link, unless there's somebody at Berkeley who objects to these kind of things, but I doubt it. So. Yeah, just feel free to email me. The classes are between 2 p.m. and 3:30 p.m. Pacific time, and then we'll start August 27th. All right, so today's topic will be, so today we want to talk about Ricci flows in higher dimensions. Let me start simple. Let me just start with a motivation and history slide. So, in the following, I'll be concerned with Ricci flows. So this will always be a smooth family of metrics on a mostly compact manifold, and they satisfy the Ricci flow equation. And so this is the Ricci flow equation. So this is something like a heat equation for the metric. So if you write it in suitable coordinates, then it looks like a heat equation for the metric. And the hope is somehow that the Ricci flow improves the metric as you move forward in time. But there are many problems that arise, for example, singularities and so on and so further. And as you may know, in dimension 3, the Ricci flow was a very powerful tool because it was used to prove the Poincarean geometrization conjecture by Parabolic. So my goal is to try to understand this Ricci flow in higher dimensions now. And so maybe let me summarize what are the important questions in the field of Ricci flow. Well, they mainly boil down to two questions. So first of all, we want to understand the singularity formation of the flow if it develops a singularity in finite time. And that does happen quite often, probably. And then if it doesn't develop a singularity, we would also like to understand the long-time asymptotics of the flow. All right, and so this was done by Parabolic basically in dimension 3. And understanding these two asymptotics allowed him to construct a Ricci flow with surgery and prove these two conjectures. Okay, so how do we normally analyze singularities? Well, we do this via what is called a blow-up analysis. And so let me just briefly recall this. So what I've drawn here is the manifold, somehow the axis to the right, and the axis to the that goes up is time. So this is some of the space-time of a Ricci flow. And what we want to choose there is a sequence of points that run into a singularity. So to be precise, those are points and times, xi, ti, so points in space-time. And ti should go to the singular time. And we can somehow say that the points become more singular by the fact that the Riemannian curvature blows up at those points. Okay? So we see these points, they run into the singularity. And then we hope to find rescaling factors, lambda I going to infinity, such that if we look at the parabolic rescalings, so we rescale the flow, that means we rescale distances by lambda and time by lambda squared. That's how the Ricci flow equation scales. And if we point the flows at the space point xi, ti, then we hope that we have convergence to some limit, which we call the singularity model. Okay. And so if you just try to imagine this intuitively, you take the flow pointed at this time, and then you blow it up. Then somehow the time interval gets bigger, and then in the limit you obtain a flow that exists for all non-positive times. So for minus infinity to 0. So that's called an ancient flow. Okay? And so then the hope is to maybe classify the singularity model. And once we've classified them, we somehow understand the local geometry near these points, because the geometry in a way converges to the singularity model. So then the singularity model can be somehow observed locally in an approximate sense. And so then we could probably repeat this process for different sequences of points going to the singular time. Okay? So this is somehow the approach that is taken very often, but I also wanted to mention that so far, in order to make this work, we need a certain curvature bound. So it's not so easy to choose these points in order to ensure that we have convergence here. And so I'm going to show you an improvement later as well. Okay, so next let me just review what we know about singularity formation and Ricci flow and blow-up analysis. So maybe we start with dimension 2. So in dimension 2, there's only one or two manifolds, S2 and RP2, that admit a singularity, or where the flow develops a singularity. And in these two examples, the flow just becomes asymptotically round modulo rescaling. And so the singularity model is just the round shrinking two-sphere. So I've normalized this so that the singularity of the singularity model occurs at time 0. So this is just a round sphere that linearly shrinks down to a point. So it comes from minus infinity and shrinks down to a point at time 0. Okay, so this was done by Ben Chow and Richard Hamilton. And then in dimension 3, things get more hairy, and Perelman found out that singularity models or blow-up limits are so-called kappa solutions, and they can be understood further. So I won't go into the details here. Okay, so the next thing that we need to that I need to recall are in relation to singularity formation are gradient shrinking solitons. So let me just briefly say what they are. So a gradient shrinking soliton is a Riemannian manifold plus a potential function that satisfies this equation here. And the potential function could be constant, in which case the equation is just the Einstein metric for a positive Einstein constant, or it could be something else. So, so if you have an Einstein metric of positive Einstein constant, then the Ricci flow will contract that and it will develop a singularity in finite time. And so this is in some sense a generalization of the Einstein condition. And so more specifically, if we write down a family of metrics as follows, so we take the pullback of a metric by a certain family of diffeomorphisms, and then we multiply the metric by t. And so I'm only interested for negative times here, so that's how I'm going to how I'm normalizing this flow. Then phi should be the flow of the gradient of f. So then I obtain a Ricci flow. So this Ricci flow is ancient, so exists from time minus infinity to 0, and its curvature behaves approximately like C over T, at least if in the compact case. Okay, so this is called a type 1 curvature blow-up. So this flow develops a singularity at time 0. And if we're interested in the singularity model of the flow, then the singularity model is itself. So this is a self-similar flow. If we rescale, we just see the same thing again. Okay. So now we would like to understand sorry, what I should say is gradient shrinking solitons are candidates for blow-ups, so for blow-up limits, singularity models, and they always occur. So then let me now talk about results that we know in higher dimensions. So in general dimensions. So for example, if we impose a type 1 curvature condition, so that means that the curvature should just behave like C over the remaining time. So that's the same curvature condition as in a gradient shrinking soliton. Then we indeed, all singularity models are gradient shrinking solitons. And so this was done by Sesson, Neighbor, Enders, Buzang, Miller, and Topping. So in this case, we obtain a good classification of all the blowups in the singularity formation. And then some of this was also generalized by myself, Chen. There's also work by Hallgren, Wang, and Chang to the setting where the scalar curvature is only the scalar curvature satisfies a type 1 scalar curvature blow-up. So in this case, the singularity models are still gradient shrinking solitons, but they may have a singular set that has codimension 4. Okay. So of course these are this type 1 scalar curvature bound does actually occur on a Kähler-Ricci flow in a Fano manifold. But other than this, curvature bounds don't really occur as something that's given. This is just something we impose to study simpler cases. So we would still be interested in the case where we don't have a curvature bound. And so there is a conjecture which I don't really know who to attribute it to, but so that's why I call it the folklore conjecture. You know, it's not a very specific conjecture. It just states that for a general Ricci flow, most of the singularity models should also be gradient shrinking solitons. So at least there should be at least one blow-up limit in a Ricci flow that develops a singularity that is a gradient shrinking soliton. And so this conjecture has been around for some decades and in several forms, and has encouraged a lot of this research. So what's the goal of this talk? Well, it will be to verify this conjecture in a certain sense, and I hope that after the end of this talk, you'll agree with me that this is possibly the optimal sense, modulo some details. And yes, of course, if you have questions, please interrupt me. All right, so these are the positive results. Let me now discuss 3 examples in higher dimensions that give us a feel what we are about what we have to expect. So the first example is a construction due to a graduate student of mine. His name is Alex Appleton. And in this example, he constructs Ricci flows in dimension 4, whose blow-up limits are one of the following 4, are the following 4 models. So first of all, we can obtain the Iguchi-Hansen as a blow-up limit. Then if we choose different rescaling factors, we could obtain R4 modulo Z2. So that's a cone over a flat cone over RP3. And then there may be, we may also obtain the Bryan soliton modulo Z2 or RP3 as a blow, cross R as a blow. So that's like the cylinder modulo Z2. So these, so I've put the last 2 singularity models into parentheses because it's, in this construction, it's not really clear if all or some of these flows actually also show these last 2 singularity models. But for sure, if we choose the blow-up sequence correctly, then we see the first 2 singularity models. And so let me just digest. So what we're seeing here, so these 2 spaces are Ricci flat. So the singularity model is just the constant flow. And then these 2 spaces are singular. So they have a singular point. Are modeled on R4 modulo Z2. And then, well, if we ask, like, in what way does this folklore conjecture hold? Well, then the only gradient shrinking solitons are these 2 guys. Okay, so and it's conceivable, I would say it's still a conjecture that there are cases where these 2 blow-up models don't occur. So it is conceivable that this is the only gradient shrinking soliton that we see. And well, you may say, well, this seems like a constant flow. It doesn't really shrink. Why is it a gradient shrinking soliton? Well, well, yeah, it is constant under the flow, but the metric itself is also self-similar basically because it's a cone. So this is kind of yeah, some very borderline gradient shrinking soliton. So it's a gradient shrinking soliton and a steady soliton and a Ricci flat and so on because it has a self-symmetry. And of course it's singular. So then there's another interesting work by Maxwell Stolarski who constructed Ricci flows, I think in dimension n bigger or equal to 13, whose only gradient shrinking soliton blow-up limit is a Ricci flat cone. So the only candidate that somehow would verify on this folklore conjecture would again be a Ricci flat cone. And of course, that's blow-up limit would be singular. And then lastly, there's an example by Li, Tian, and Zhu, where they show the existence of a Kähler-Ricci flow that has to develop a singularity, but due to reasons relating to Kähler geometry, the blow-up limit cannot be a gradient shrinking soliton because they somehow don't exist on this manifold. So this also has to develop a, and so it can be shown that this, in this example, the limit is in fact a gradient shrinking soliton with a singular set. Okay, so well, what's the conclusion of this slide? Well, it is that if we want the folklore conjecture to be true, then we have to allow a singular set on these gradient shrinking solitons. And we may have to allow, we also have to allow Ricci flat cones as blow-up models. We have to accept that those are gradient shrinking solitons. Are there any questions so far? Okay. So the goal of this talk will be to show you, maybe I should say, some of you, if you see these blow-up models, may be reminded by this picture of the somehow the compactness and partial regularity theory of Einstein metrics. And in fact, what I want to show you later is that Ricci flows basically almost behave like Einstein metrics, and that there is a very similar theory of compactness and partial regularity. And so in order to do this, let me just first recall what we know about Einstein metrics. So you don't need to understand every single detail to the full extent, but I just want to give you a feeling what we know about Einstein metrics, and then I'll talk about Ricci flow. All right. So let me consider a sequence of pointed and complete Einstein manifolds. So Mi, Gi, Xi. So the Einstein equation is this equation. So the Ricci tensor is a multiple of the metric. And then I'll just normalize the Einstein constant. You can also think of Ricci flat that if you want to simplify things. So what do we know? Well, first of all, we know that the Einstein condition implies that the Ricci curvature is bounded from below. So we can pass to a subsequence, and we have Gromov-Hausdorff convergence to a pointed metric length space. Okay, so the limit is going to be a metric space, and so it's a length space. That's the additional structural information that we have. And of course, there are many different metric spaces. So we would like to get some additional information. And there are also many things that could go wrong. So we could take a compact manifold, we could scale it down, and we could get a point in the limits. Or we could get some space of lower dimension. So we have this phenomenon of collapsing that we have to rule out first. And so this is ruled out by often a non-collapsing condition, and that's a relatively weak condition where we just require that the volume of a ball of fixed radius has a fixed lower volume bound that's somewhat independent of I. Yeah, so this is often called the non-collapsing condition. And so now if we assume the non-collapsing condition, then it turns out that the limit is actually very nice and regular. More specifically, we can decompose the limiting metric space into two subsets, a regular subset and a singular subset, such that the following is true. So the regular part is actually an open manifold, and there's a smooth Einstein metric, I'll call it G infinity on R, that is somehow locally isometric to the metric. And it's, which is due to Cheeger and Colding, that not only is this Riemannian metric isometric, but it's also its restriction to its length metric is equal to the restriction of the metric on X to the regular part. So in other words, if I take 2 points in the regular part, then the distance between those 2 points is actually realized as the infimum over lengths of paths between those 2 points. Right? So that's a very strong result. And this implies, amongst other things, that the metric space is actually isometric to the metric completion of this incomplete Riemannian manifold. So in summary, we take this very synthetic limit, x dx, and it turns out that this synthetic limit can actually be completely specified by specifying a smooth Einstein metric on an incomplete manifold. All right, so R completely describes X. So what do we know about the singular part? Well, the singular part is very small. It has Minkowski dimension less than n-4, so codimension at least 4. So that's due to Cheeger, Colding, Tian, and Neighbor. And so that's a pretty strong bound. So that's even stronger than Hausdorff dimension. And then we also know that any tangent cone at any point of x is a metric cone. That's due to Cheeger and Cole. So, so a tangent cone is a Gromov-Hausdorff limit of a sequence of blowups pointed at the same point. So it has the name cone as the word cone in its name, but a priori it's not clear if it's actually a cone. So, but in this case, indeed, it's a metric cone. And then there's a further stratification result due to Cheeger and Neighbor. So there's some kind of filtration or stratification of the singular part. And it has some nice dimensional bounds. And as we go up in the dimension, these points have tangent cones that have further symmetry. So they split off RK factor. So this is maybe not so important for this talk, but there's somehow a good understanding of the structure of the space. Are there any questions on this? Okay. So, so similar theories exist for minimal surfaces, harmonic maps, mean curvature flow, and harmonic map heat flow, and so on and so further. And basically, I could show you the previous slide, and I would just have to change the words, and maybe like the dimension is slightly different and something like this. But there hasn't been a theory like this for Ricci flow, and so this is what I want to show you in the following. So let me make a few key points. So I'm going to show you a slide where there's a lot of new information. So I hope you're not going to be scared. But so let me just make the key points first so that you know what we're getting into. So the key points are there's a compactness and partial regularity theory for Ricci flow that is comparable to that of Einstein metrics. And this theory will allow us to establish the folklore conjecture and several other related results. And so in order to state this, we of course need new parabolic versions of notions such as metric space, Gromov-Hausdorff limits, Minkowski dimension, and so on and so further. So I will have to introduce them too. And so the way I hope that I can present this in the best way is I'm going to state the main compactness theory, and then I'm going to mark all the new words in red, just to show you that I'm aware that I haven't introduced them. I hope you can take a little bit away from this theory, just intuitively. And then later in this talk, I'm going to explain what these words mean. All right, so here is the main result. So let's consider a sequence of n-dimensional pointed Ricci flows. So I'll denote them by this. And for reasons that will become clear later, I am interested in Ricci flows that are parameterized by a time interval from -ti to 0. So the final time should be 0. And I always imagine that my base point lives in the final time slice. And then T infinity should just be the limit of the TIs. Okay, so I have these Ricci flows. And then my claim is that there is a subsequence of these flows that F converges to a metric flow X equipped with some new X. And so I'll write this as using this F on the arrow. And so again, this metric flow could a priori be collapsed. So I have to introduce a non-collapsing condition. And the non-collapsing condition will now be a lower bound on the pointed Nash entropy at the base point as a uniform lower bound. And so, let me just briefly say this is a bound that almost always exists in our applications. So for example, it is implied by a lower bound on Perelman's mu functional. It's implied by a lower bound on the volume of a ball, just like in the previous slide, and so on and so further. So so this is going to be a condition that's the condition that we want here. So now let's assume we have this non-collapsing condition. Then again, we have a regular singular decomposition of the limit, and we have the following properties. First of all, X is restricted to this regular set is given by what is called a smooth Ricci flow spacetime structure. So it's a very regular object. And X is actually uniquely determined by the structure. So X actually arises by taking just a nice completion, like a completion of R, just as before, where we took the metric completion. And I'll explain this later. Then the singular set of this flow, again, has codimension 4. And here, as in many other parabolic problems, we have to count the time direction twice. So we get 2 points for the time direction. So that's why it's n+2 - 4. Then in the place of tangent cone is now taken by tangent flows. So And though the tangent flows of X are going to be gradient shrinking solitons. So this is now the parabolic version of a metric cone. You know, gradient shrinking soliton is again self-similar. If we rescale it, we get the same thing. So that's the same, that's also true for a cone. And then again, we have a similar filtration result. And here we have to also account for the possibility that we see a symmetry in the time direction, in which case our blow-up is static and only splits of an RK-2 factor. And that's again very standard for parabolic problems. All right. Are there any questions on this? I mean, I know I haven't introduced the red words, but apart from this. Okay. So what I'm going to do in the next slides, I hope you have a little bit more patience. I want to show you some of the consequences of this theory. And then in a few slides, I'm going to give you an introduction of what these red words mean. Okay, so what's the first consequence? Well, let me address the folklore conjecture. And I'm going to state this in a more vague way. It's a bit harder to state, but you'll see hopefully later that it makes sense in a certain way. So let me consider a Ricci flow that develops a singularity in finite time. Then I claim that there is a certain metric space which arises as a limit of the time slices as you approach the singular time. And this metric space has the following properties. So first of all, if the metric smoothly converges to some Riemannian metric locally, you know, if the singularity happens to not occur in a certain region of the manifold, then essentially the space is just that metric. So, you know, it's locally isometric to whatever you converge to. As it should, sorry, this should be a capital T. And then moreover, for every point in this somehow asymptotic time slice, there is some blow-up sequence of points that converges to this point in a certain sense. And the blow-up sequence of this point, if we choose the factors appropriately, there's a very clear choice, then we obtain a singular gradient shrinking soliton. And vice versa, some blow-up sequence with some of the right rescaling corresponds to a point. So this basically gives us somehow some of the set of all possible gradient shrinking solitons almost. And in a way, we can view singularities here as a tangent flow based on C. Okay, so I know this is a very vague, but I just want to show you that this can be done. Next, let me just briefly address on a small improvement. So what do we know in dimension 4? So that's the first dimension that where the theory becomes interesting. So in dimension 4, all singular gradient shrinking solitons that I've told you about, they're actually given by you know, this data MGF, where M is an orbifold with conical singularities. And so it's a very simple object. It's a C infinity orbifold that's a gradient shrinking soliton. And moreover, either we have positive scalar curvature on this orbifold, or our space is just going to be a quotient of our 4 modulo some finite group action. So it's some cone, some flat cone. And so this, you know, somehow this somehow agrees with the results of Appleton and Stolarski and so on. All right, if there are no questions, let me move on to the next result. So let me address long-term asymptotics. So let's assume that we have a Ricci flow that exists for all times. So that is called immortal. So it exists for time from time 0 to time infinity. And let me consider a sequence of points that run out to infinity. So the times go to infinity. And I want to understand what somehow the geometry near these points. Then my claim is the following. After passing to a subsequence, we see one of two behaviors. Either we can blow down, so we rescale the flow down parabolically. And if we do this and take the base points at xi, then we converge to a singular Einstein-Ricci flow with negative Einstein constant. And so this is what we would expect. And so this is what was shown by Perelman in dimension 3. So in this case, of course, the limits were hyperbolic. And then if the dimension is 4, then the flow is again given by an Einstein orbifold. Or if we somehow pick the points differently, then we may see collapsing. And this is can be observed by this Nash entropy. And I'll maybe can cover this also later. All right, so let me briefly apply this theorem. So what's the picture in dimension 4? Again, the first time things become interesting. Well, in dimension 4, if you choose a very large time, then we can actually decompose the manifold into what is called a thick part, and then an almost singular part and a thin part with the following properties. So on the thick part, the metric is almost Einstein. The almost singular part consists of components whose boundary are spherical space form of very small diameter, so they correspond to these orbifold points. And the thin part is locally collapsed. So you can either state this using the Nash entropy, or for example, this would also imply that volumes of balls of the appropriate scale are very small, so smaller than we would expect, so they collapse. So this is basically really what we understand by collapsing. Okay, so this is exactly the picture we get in dimension 3, modulo these almost singular points. Okay, are there any more questions? Okay, so let me also show you, so all the theorems that I've shown you so far, they involve some convergence, and I didn't really tell you what the convergence is. So to show you that I'm not cheating here, here's an application which is completely elementary and which hasn't been known before, and it's called a backward pseudolocality theorem. And it states the following. So let's assume our flow exists on some time interval from t0 minus r squared to t0. So, somehow. Let's assume that we take a ball of radius r, and we assume that its normalized volume is bounded from below by some alpha, so it's not too collapsed. And we also assume that at that time, t0, we have a curvature bound. Then the theorem states that we can extend the curvature bound backwards in time on a smaller ball. And so this theorem is called the pseudolocality theorem. So it was named by Perelman, who proved a forward pseudolocality theorem. So the assumptions are exactly the same, but the assertion now in Perelman's theorem is that you have a curvature bound forward in time on a smaller ball. Okay, so so now this completes this picture. There was also previous work of myself and Ji Zhang, I should say, in the case of bounded scalar curvature, but somehow this removes this assumption. Okay, so again, this shows, I hope this demonstrates that this theory is somehow useful and can be used for certain things, even if you don't like F convergence. Here are some further remarks before I continue. First of all, in dimension 3, this theory essentially recovers Perelman's theory. So we more or less get everything that Perelman could say about the flow. We have to be a little, do a little more work to say that these flows are good, these limits are non-singular, but this can be done relatively easily due to the high codimension. And then there's also a corresponding compactness theory, not assuming, so somehow the first part of that theorem, where I only say that you converge to a metric flow if you have a super Ricci flow. And so that's very analogous to this case of spaces with non-negative Ricci curvature, because in that case you also have Gromov-W convergence. All right, so those should be all the results that I wanted to show. So in the next few slides, I want to give you an overview what these limits are, and I'm going to try to explain some of those words. But maybe before I continue, are there any questions or anything I should clarify? Okay, let me just see who's actually here. I hope I'm getting that right. Okay. Yeah. Okay. Then, okay, so let me give a little bit of a background. So what I want to cover in the next slide, just want to explain to you heat kernels on a Ricci flow background. So it turns out that understanding this is a very integral to this whole compactness theory. So I want to recall things. So so let's first consider a Ricci flow, and let's just fix the Ricci flow. And I'm going to be interested in in smooth or C2 functions, I'll call them U and V on this Ricci flow. So they're just going to be functions on the spacetime. And so then there are two equations that are going to be interesting for us. First of all, there's the heat equation. I always assume that U satisfies the heat equation. So it's just that the time derivative of U is equal to the Laplacian. And the important thing is that I take the Laplacian with respect to the metric at that particular time. So it's a time-dependent Laplacian. And then there's the conjugate to the heat equation. I'll denote that by box star, where I take the conjugate of every single operator, and due to somehow the distortion of the volume form, I get this extra scalar curvature term. Right? And then if I talk about the heat equation, there's also a heat kernel of this heat equation. And I'll denote this by kx comma t, semicolon ys. So s should always be less than t. And so what's the definition of the heat kernel? Well, if we fix ys, then this looks like a heat kernel placed at the point y at time s. So if we fix these parameters, then the first two parameters should satisfy the heat equation. And if the time goes to, if t goes to s, we should converge to a delta function. And if we fix x and t, then we can apply a duality argument, and we obtain that these the second two parameters actually satisfy the conjugate heat equation. Okay, and we again limit to the delta function. Okay, so this is a very nice object. It somehow encapsulates both the heat equation and the conjugate heat equation. And then with this heat equation, there are representation formulas. So if we look at solutions to the heat equation or the conjugate heat equation, then we can somehow represent the heat equation in this integral way by this convolution with the heat kernel kind of integral. It's not really a convolution, sorry. And the heat kernel satisfies a reproduction formula. So meaning if I take 2 times s, t prime, and t, then I obtain the heat kernel between times s and t by integrating over the time t prime slice and the product of both heat kernels. Okay, so I expect that you've seen some of these, partially at least, in a certain setting. Okay, so what are the properties of the heat equation? First of all, due to the maximum principle, upper and lower bounds to the heat to U are always going to be preserved. And then due to an argument involving the Bochner formula, also gradient bounds are preserved. Okay, so if my function is Lipschitz, then it remains Lipschitz with the same Lipschitz constant. And so now here's an important improvement of this result, that we actually get some kind of improved gradient estimate. So here's what I want to state. So let's consider a solution to the one-dimensional heat equation. I'll call that phi. It should exist for all non-negative times. And it should start, the initial condition should just be a step function. I think it's called the Heaviside step function. So I've drawn a picture here. And then it should just evolve by the heat equation. So it looks like, the integral of a Gaussian. So in theory, this is a heat equation on a Ricci flow background, a one-dimensional Ricci flow background. So this would be a candidate for you, of course, a very trivial one. And so now the theorems that I want to introduce to you is I call this the improved gradient estimate, and we'll encounter this later, is that basically this solution phi has the worst possible gradient. And in the following sense, so assume that I take another solution to the heat equation, I'll call it U, and U should be between 0 and 1. Then I can estimate the gradient of U by the gradient of phi, where phi has the corresponding value. So if I take U at some point and I choose x prime, such that phi has the exact same value as U, then the gradient of U will always be smaller than the gradient of phi. So phi has the worst gradient, some of the one-dimensional cases, the worst gradient. And there's also some kind of preservation property involving this equation. Okay, so even if I start with something that's not smooth, or that's not continuous, I will obtain this gradient estimate after some time. Okay, so we'll get back to this property in a moment. So what are the properties of the conjugate heat equation? Let me just address those first. Well, first of all, non-negativity of the solution is preserved. And then the conjugate heat equation now preserves the integral. Okay? And in particular, this means that if we look at the heat kernel where I fix the first two variables, so and vary the second ones, so that's the conjugate heat kernel, then this always has integral 1. Okay? And so this should lead us to somehow think of solutions to the conjugate heat equation as measures. Okay? So these are maybe probability measures in the case of the conjugate heat kernel. So I'll write them as mu s or nu s, where I take v and then I multiply it by the Riemannian metric. All right, are there any questions on this? Okay, so so what will be most useful for us is now to view solutions to the conjugate heat kernel as measures. And in order to do this, I'm going to introduce this notion of the conjugate heat kernel probability measure. Okay? So I'm not doing really, mathematically, I'm not doing very much. I'm just trying to somehow appease the math gods here by writing things down in a nicer way. And so I'm just going to set mu x comma t semicolon s to be somehow the corresponding probability measure corresponding to the conjugate heat kernel placed at x comma t and evaluated at time s. Oh, I think I have a picture here. So this is the time t. It's a conjugate heat kernel that somehow flows out of x, and then there's going to be some probability measure which I call like this. Okay, and then now I have the same formulas as before using this measure. So let me just write them down once. So a heat flow, U satisfying a heat equation is now equivalent to this equation involving a d mu xt measure. A conjugate heat flow is equivalent to a statement like this. And there's also a reproduction formula for the conjugate heat kernel measure, which takes this form. Okay. So this is the same as for the heat kernel. All right. Are there any questions? Okay. So with this notation, let me now define what a metric flow is. So again, a metric flow was the limit of a sequence of Ricci flows. So this is somehow the equivalent of a metric space. So that's why I call it a metric flow. So a metric flow over an interval is now a tuple of several objects. And I'm going to tell you what these objects are. So it's somehow surprisingly simple. So first of all, X is going to be a set consisting of points or space-time points. Then T is going to be a map assigning to every point a time. And the level sets of T are going to be called time slices. And then for every time slice, dt will be a metric. So that xt comma dt is a complete and separable metric space. And now these mu x comma s are just going to be probability measures, which I view as the conjugate heat kernel. So they should satisfy the same reproduction formula as before. And they should be the delta function at the same time, at the initial time. And then I can define conjugate heat flows as before. So let me not write the formula down. And the only non-trivial condition that I require is that this improved gradient estimate from the previous slide, from 2 slides ago holds. Okay, so this involved the gradient of phi, where we compared the gradient to u. And so now, since we don't want to talk about gradients, we'll just phrase this condition in terms of one Lipschitz functions or Lipschitz conditions. So the details are not that important, but so we can do this on a metric space. Okay. So this is for me the definition of a metric flow. And so let's digest this definition, and let me just tell you in what way we can take a Ricci flow and turn it into a metric flow. So that's somehow the main construction. So let's assume we have a Ricci flow over an interval I on a manifold M. So what's the metric flow? Well, we just set X to be the product of M cross I. Then we set T to be the projection onto the second factor. So the time slices are now going to be M cross I, just as we would expect. dt should be the length metric of the metric gt. And the heat kernel measures should just be defined as before. Okay, so now, of course, a point in a metric flow is going to be a point in space-time. So it will be a pair x comma t. All right, so let me make a few notes. First of all, I just want to call to your attention that distances between points at different time slices are not defined. And I think that's very good. So we should, there's no good definition of distances between points at different time slices. Also this construction, and this is a very important fact, this construction completely forgets world lines. So what's a world line? Well, a world line is, just like a line of this form in space-time. And basically what I'm trying to say is, well, if we take a normal Ricci flow and we view the space-time picture, so we look at this product, then we could say there's a point x at time s, so x comma s, and a point x comma t, and they correspond to the same time on the manifold, so they project to the same point on n. And this is an information that we know in a Ricci flow, just by the fact that we have fixed this Cartesian product. But on a metric flow, this information is forgotten. So, so this does not exist anymore. So this may be somehow not satisfying, but I think this you'll see later why this is a very good idea. So world lines, in my opinion, are not very useful in most Ricci flow applications. Well, maybe I should correct myself. They turn out to be useful in dimension 3, but due to other reasons. Okay, so instead of using a world line, we now have a probability distribution that says that if we have a point x and we want to say what's the corresponding point at some earlier time slice, then it's not going to be one point, it's just going to be a probability distribution of these points. So this is how I want to view them. And the probability distribution is given by this probability measure, conjugate heat kernel measure. All right, are there any questions? So again, these probability measures are the only relation between different time slices. Okay, so let me also, okay, what I want to do next is I want to discuss one further property of Ricci flow, which I think is new. And this will give us an additional feeling of what a metric flow does and this property of what's the past of a point. And so that's a concentration property. And so what I'll do is I'll make a new definition. I call this the variance. So I'll define the variance of a probability measure on a metric space. And I'll define it as follows. So the variance, I'll call it variance mu, is going to be defined as the double integral over the square of the distance function, where I just integrate against against the probability measure in both arguments. So there's a version I have where I have variance in two variables and for two probability measures, but that's not really important. Okay, so now, so here's the theorem. On a Ricci flow, we have this variance bound. So we take the conjugate heat kernel based at some point x comma t, and we evaluate it at time s. So that's just basically imagine the picture that you've seen before. And then I claim that the variance is bounded by some number hn times t minus s. And hn is this weird number here, n minus 1 pi squared over 2 plus 4. It's surprising, but this is somehow, I think, the sharpest estimate that you can get. And so whenever a metric flow x is concentrated, plus a little more, whenever it satisfies this condition, maybe plus a little more, but let me not get into this, then I will call it H concentrated. So any metric flow that arises from a Ricci flow is H concentrated for Hn, or Hn concentrated. Okay, so what do I mean by this? Let me just digest what this theorem tells us, just on an intuitive level. It tells us that somehow, again, the past of a point is given by a probability distribution. And now that we know that the variance of the probability distribution grows linearly, if you go backwards in time, of the conjugate heat kernel measure, sorry. So basically this result tells us that the past of any point is determined up to an error of t minus s. So there's somehow, some cloud of points where, up to an error of square root of t minus s, we can say what the past of a point is. It may not lie on a world line, but that's the past of a point. All right, any questions? Okay, so the next thing I need to recall, I'm sorry, I have to recall a few notions just to give you a little bit of a sense what we can do on a metric flow. Is the one Wasserstein distance. And so you may have heard of this. So what's the one Wasserstein distance? I'd say it's going to be a distance function between two probability measures on a metric space. And it's defined using one of the two formulas. So it can either be defined using couplings, where I take the infimum over the integral of the distance function over all couplings between mu1 and mu2, or it calls also, due to the Kantorowicz-Rubinstein duality, it's also defined using the somehow a supremum over one-elliptic function, which maybe is a bit easier if you've seen it the first time. Okay, so here's the fact that I think it's just folklore. Many people should probably know this about a Ricci flow, but I claim that it's also true in a metric flow. It's that if we take 2 points in 1 times lies xt, x and y, and we look at the corresponding conjugate heat kernels, then the distance between those 2 measures in the W1 sense is smaller than the distance of x and t. Okay? And moreover, there's some other monotonicity property of solutions of standard conjugate heat flows. So let me not get into this. Okay? So let me just interpret this again. So this basically tells us that distances don't really shrink on a metric flow. Okay? So in a way, if we somehow forget about world lines and we think more about these conjugate heat kernel measures, then then in the W1 sense, distances actually can only expand on a Ricci flow. Quite different from what you may expect in certain examples. So now this property now gives us a tool to define parabolic balls. Okay? So let me address parabolic balls. So let's first recall what a parabolic ball is. So let's assume that I have a Ricci flow, and I look at the Ricci flow spacetime m cross I. It's called m cross I at the space time picture, and I just want to define a ball within this spacetime. And some of the standard way of doing this for many decades now has been to define this spacetime ball as what's called a parabolic ball as follows. So we take a point and a time, and then we consider the ball with respect to the metric at that time around that point. And then we just take the Cartesian product with the corresponding interval. Okay? So here in this figure, this is time t naught. You look at the point x naught. You look at this ball here, and then you're just going to take the Cartesian product. And of course, this is a construction that completely relies on world lines. So in a metric flow, such a construction is not possible. Instead, what we'll do is we'll consider, I'll define a new notion called which I call P star parabolic balls. So what's a P star parabolic ball? So it's denoted like this. So for a point x naught, I'm now going to look at the conjugate heat kernel, and I'm going to include all points that are somehow within the same time interval, and where somehow the conjugate heat kernel at that earliest time has W1 distance less than R from the base conjugate heat kernel. So this is going to be my P star parabolic neighborhood. That's somehow the most natural way to define a parabolic neighborhood on a metric flow. And it turns out that this is a very useful definition. So for example, standard containment properties still hold on P star parabolic balls. So if you increase the radius, P star parabolic ball gets bigger and stuff like this. If we have curvature bounds and we are in a nice Ricci flow, then conventional and P star parabolic balls are going to be comparable. So up to some constant in the radius. And the natural topology on X, now we can define a natural topology on X, which is just being generated by all these P star parabolic balls. And also the P star parabolic balls allow us the definition of a parabolic Hausdorff and Minkowski volume and dimension. So, and this is the one that occurred in the theorem. Again, we count the time direction twice. All right, so I only have 5 minutes left. Let's see how I where I can get. Are there any questions? So I think that in the last slide, in the last few slides, I'll just discuss F convergence briefly, because that was one of the notions. And maybe I'll say a few words about Ricci flow spacetimes. Okay, so in order to understand F convergence, so the convergence, again, that was the convergence of Ricci flows to a metric flow, I have to introduce what I call the Gromov-W one distance, and I think other people call it differently. And this is the following. So assume we take, so it's an analog of the Gromov-Hausdorff distance, and it's defined for metric measure spaces. So metric spaces equipped with the probability measure. And it's defined as the infimum over the W1 distance of the push forwards of these two probability measures, where the infimum is taken over all isometric embeddings into a common metric space. So really, I've just replaced the Hausdorff distance here by the W1 distance. And it's the same definition as the Gromov-Hausdorff distance. Okay? And then, you know, whenever this distance goes to 0, we say that we have Gromov-W1 convergence. Okay? So here is an important observation that I want to make. So this convergence is defined for also unbounded metric measure spaces. Okay? But if you wanted to define the Gromov-Hausdorff convergence for unbounded Gromov-Hausdorff convergence for unbounded metric spaces, you always have to choose a base point. Okay? So otherwise you don't know, you know, the sequence may somehow run off to infinity. But this is not necessary here, because here we're looking at probability measures, and probability measures always tell you somehow, in an approximate sense, where somehow the center of the metric spaces. Okay? So the probability measures take the role of the base point here, and that's somehow that's an observation that I want to apply in the next slide. Okay, so now let me define the F distance, and I think that's probably going to be it. So what's the F distance? So I want to now define something like a Gromov-Hausdorff distance. So, but not between metric spaces, but between metric flows. Okay, so this should allow me to say what convergence of Ricci flows means. And I'll do it as follows. So I'll consider, let me consider two metric flows. And I now have to equip these metric flows with conjugate heat flows. So there's going to be families of conjugate of probability measures in every time slice. And now I'm going to define the F distance between these two pairs to be the infimum over all radii R. And now things are getting a little more complicated, such that there are isometric embeddings for every time t, except for times in some set E, into some common metric space, which may depend on t, with the following properties. So this exceptional set, where we don't need to have isometric embeddings, should have small volume, or small measure. Then I want the push forwards of the two conjugate heat flows to be close in the W1 sense within this ambient metric space Z. And I need some kind of integral closeness of the corresponding conjugate heat kernels so that they also in a way match up. So let me not get more into the details. Yeah, I'll post the paper soon so you can read it. And it somehow it's probably what you would want to do, or one of the options. Okay, and then again, if the F distance goes to 0, we say that we have F convergence. Okay, and so, okay, so this, there's a lot of definitions. So let me just, emphasize that F convergence implies Gromov-W1 convergence at almost every time. So it's really not such a bad notion of convergence. All right, so, and now it turns out that for F convergence, we have basically the same theory as for Gromov-Hausdorff convergence. So let me, for example, denote by F the space of these pairs, a metric flow and a conjugate heat flow. Then we get that the space and the distance function is actually a complete metric space. So just as the space of isometry classes of metric spaces and the Gromov-Hausdorff distance is a metric space, we complete metric space, this one is as well. Let's suppose our time interval looks like this. Then we also get that the space of these pairs of metric flow and conjugate heat flow corresponding to Ricci flows is actually pre-compact within this metric space. And so as a corollary, we obtain compactness theory of the conjugate heat flows. of Ricci flows and you know, subsequential convergence to a metric flow in the F sense. Let me just make another remark. So actually, this theorem up here can be phrased in a nicer way, where we can exhibit a very easy to define compact subset to which all these Ricci flows belong. So it's very, very analogous to the theory of a Gromov-Hausdorff convergence. Okay, so maybe I hope I can take one more minute. Let me just digest this F convergence, and then maybe I'll stop. To just show you a few of the interesting things. So first of all, I just want to state, if we assume curvature bounds, so that's the setting in which we normally can use to subsequence or study convergence of flows. So in this case, F convergence is more or less the same as local smooth convergence in the sense of Cheeger, Gromov, and Hamilton. But here's another example, which I think is more interesting. So let me consider the Bryan soliton. So this is a rotationally symmetric solution to the Ricci flow. And the time slices are all, so it's a steady gradient soliton. So all the time slices are isometric. And the time slices are, you know, take this warp product form. And so the warping function here grows like square root of R. So these things don't open up conically. They are also not asymptotic to a cylinder. They still grow like square root of R. And so now let me take a base point, somehow at time 0. And at the tip here, and let me take a sequence of blowdowns. And I want to know what the limits are. And so I'm going to scale this flow down. Okay. So first of all, you know, I could take the good old Gromov-Hausdorff limit at any fixed time. So I would have to fix a time, and I would have to understand its Gromov-Hausdorff limit. And so since this, since this thing opens up like square root of R, the Gromov-Hausdorff limit is just going to be an array. So now here's the question. So what's the F limit? Yeah, so I guess we can't really do question and answers. So maybe you can take a guess what the F limit is. Well, the F limit turns out to be surprisingly the round shrinking cylinder. So this may be surprising, but in the end, this is exactly what we want, because this is the asymptotic soliton of the Bryan soliton. So it turns out, you know, as just to recall, we're taking F limits by considering conjugate heat flows as somehow the, as a way of telling us where the center of the manifold is. And conjugate heat flows, sorry, they end up just flowing out to infinity here at a certain rate. And if we look somehow in the area where these conjugate heat flows are concentrated, the manifold looks more and more cylindrical. And this is also called the asymptotic soliton by Perelman. So the F limit really recovers the asymptotic soliton. So maybe, I'm sorry, I'm over time. I'm going to stop here, but if there are questions, I can show you some other slides, or whatever you're interested in.
All right.